Okay, so let's start from where we left in the last class, right? This is the point where I have started basically the internal coordinates for the ammonia, right? So using this, we generated the, and also using the Cartesian coordinates, we generated the reducible representation for these, right? So let's just quickly do it, and then we should be able to find it out, right? If you recall this, I think this was 3, right? And then this was 0, and this was 1, right? Then this was also 3, 0, 1, and the irreducible representation, they span like E1 plus E. Right? Now, similarly, this is going to be also A1 plus E. And of course, the total is going to be 2A1 plus 2E, right? So that's what we found it out, right? And then we try to figure out what are going to be the normal modes. Let's go quickly. Yeah, so that was the symmetric bending, and what we tried to find out what is going to be the symmetry of this, or that is irreducible representation, and whether it was IR active or Raman active or not, right? So of course, if you look at this is a symmetric bending. Q goes along this, so they remain all invariant under all the symmetry operations, right? So therefore, this was E1, and it was both IR and Raman active depending on their Cartesian coordinates and the quadratic term, so that you can look at from the character table, right? So E1, so Z transform as E1, so therefore it is IR active, and these quadratic terms like x square plus y square and z square, that they also transform as like A1, so that was Raman active, right? Now we add it for symmetric stretch. Symmetric stretch is also exactly in the same way. We get 1, 1, 1, and that is A1, and it's both IR and Raman active, right? Then if I recall correctly, the last class we left at the place where the asymmetric stretches are going to be, right? Now this asymmetric stretches is basically, there are two of them, like one of them you look at here, this is one of the NH bond, this another, they are in the same phase stretching, and the opposite phase, the other one, third one is going to be the opposite phase, right? So that is asymmetric stage, and this goes along minus AX. Like here, like this is again, like as I said last class, this is along like a water molecule. Like if we don't think about this, this is not participating, so this is in combination the opposite phase, and this is minus y direction, right? So they go along different directions. So now if we combine both of them, we need to combine both of them because they transform simultaneously, they are not independent. So therefore, if we go like this, so the number what we get for asymmetric stage, that is going to, identity is going to be 2. Now for C3, of course, the way we have discussed is that like this is like minus x, this is minus y. So contribution from each of them is from cos theta. So cos 120. So that is minus half, so that is going to be minus 1. And sigma b, of course, if we do xz, then this remain unchanged. So that is contribution from this one, because this is on the xz plane. But in this case, minus y goes to plus y. So that is minus 1, right? So overall, I get 0, right? And therefore, this is going to be doubly degenerate representation E, right? So now we have to find out what is the E representation. So E representation is this one. Now you can look at here both x and y, they simultaneously transform along E. So therefore, this is going to be IR active. Right? So that is IR active. Right? That's what we discussed in the last class, and also this quadratic terms goes along E. So therefore, it is also going to be Raman active. Right? So this mode is also both IR and Raman active. Now, what about the asymmetric bending, or like let's look how they this one, right? Now this one, if you look at, so this is kind of, this angle is scissoring, but this is going up and down, right? But resultant is going to be along again minus x, right? Now if you look at this one, this all of them are participating. This is amplitude is more along this, and then this is this one, this is this one. So resultant is going to be like this. So that is kind of y, right? So now if we take both of them simultaneously, again I just kept it because it's going to be same. So therefore, like 2 for identity, each of them 1 plus 1. Now C3, again contribution is cos 120 from each of them, so that is minus half, right? Minus half, that is minus 1. And then in this case, like again this remains unchanged, plus 1, and this is going to change. So that is going to be minus 1, total 0. So this is doubly degenerate representation, and therefore again this is going to be IR and Raman active, right? So that's what all the normal modes, and I just take the liberty of the PowerPoint and made all these modes using calculating them, such that it gives you better visualization. Drawing on the 2D scale may not be that clear. Anyway, so that's what is that. So what we get in the summary is that, so 2 of them are E1 normal mode, so that is asymmetric bending or wagging, whatever you say, and the asymmetric stretching, right? So both of them are symmetric, a totally symmetric representation. They go along A1, and therefore we got total 2A1. Now 2 of the bending, like here what we get, they go along A, and again 2 of the asymmetric stage also go along A. So total 2A1 plus 2A, so that total 6, and that gives you the symmetry of the normal modes and their IR and Raman activity. So all of them are both IR and Raman active, right? Now, yeah, so now here I want to again ask you that, like, if we can take one example and do it yourself, right? So I think simplest one would be, let's say, CHCl3, right? So that is CH, then if we go for Cl, chlorine, right? Now if we take this is again C3V, right? So exactly the same way I asked you to do it for the Cartesian coordinates using the x, y, z, right, on each atom, x, y, z on each atoms, right? So we find out what are going to be the normal mode symmetry, right? And then go for the bond coordinates, right? Now here bond coordinates are going to be 4, and then you have the angles. You have 6 angles, so you figure it out how they are going to be. So that is basically for bond coordinates. Right. So if you take bond coordinates, I'm not writing in full, then take again the find out again the normal modes and try to compare them, how they are going to look like, right? Or is there any missing mode, or is there any extra mode is coming in? So that should be you should be able to figure it out. Okay. So that's what about like I wanted to do it for the normal modes. We will be discussing this in more details in the another course, that is 307, right? So for the time being, I think if you understood this much, then that should be good enough for your GATE and NET exam. You'll get a couple of questions from this place, right? Okay, so now let's change the gear, and what you guys were asking for, let's go to the some idea about the SALC, right? Symmetry adapted linear combinations, right? So I hope we'll go this a little bit slowly such that you can understand better. Okay. So that is symmetry adapted linear combinations. By name itself, you can understand that these linear combinations are based on symmetry, right? Now, how do we do that, and how it look like? So that will be in a due course of time. So before getting into that, I hope this linear combination of atomic orbitals, LCAO, this was taught by Dr. Rakhi, right? So he must have given you a lot of idea how it has been it has to be done. But as there is a gap between this class and the previous class, so let me give you a little bit of introduction on this linear combination of atomic orbitals, and then we introduce what is the symmetry adapted about that, right? Okay, the simplest example, if we take like a hydrogen atom, sorry, a hydrogen molecule, right? Let's say this is atom A, and this is atom B. Okay, now the way we did linear combination of atomic orbitals to form the MO is that we took the atomic orbital 1s of this first atom, so that is A, and then we took the 1s B, B stands for the second hydrogen atom, right? Then what we took, there are possible combinations, like it can be plus minus, and then we did that. So that means what we took, like our guess function for MO, right, is going to be linear combination of this. So that is, let's say C1 or CA, whatever you want to get it. Then this is going to be C2, right? So we took this linear combination of these two atomic orbitals, and then we try to find out what is going to be the energy using this. So that is nothing but your something like psi mo gas, so that is actually gas. Then I'm having the Hamiltonian here, right? I hope you recall from this Roxit's class. So writing is difficult on this, but and then bottom you have the overlap integral between this. Right. I hope you recall this. Even if you don't recall it, we're going to explain a little bit what is going to be. Right. So this is the energy. So now when we write this, now if we replace in terms of these coefficients, right, then what happens? Like and evaluating this integral, you will get a set of equation, right? So therefore you get something like here, as I am having two atomic orbitals combining, so I get 2 by 2 secular determinant. I think that's what you remember. How do you do this? Now in this expression, right, you replace this here, here, and also here, and also here, right? Once you replace this, then what happens? Now this energy is basically going to be a kind of I won't say function, it's called functional because it's not direct dependent, because it's a C2, right? So this is called the functional. The reason is that the C1, C2 is coming through psi mo, and that in turn getting into this. So now why is it so only functional of C1 and C2? Because one is A, one is B, they are orthonormal function, right? So therefore, if there is overlap, that should be a 1. If it is not, that should be 0. So ultimately, you will get this expression you will get in terms of the C1 and C2. And then what we do, we do the to minimize this energy to get the best possible wave function, to get the coefficient, we minimize this with respect to the coefficient C1 and C2, right? So that means what we do the derivative of this with respect to C. I stands for can be 1 or it can be 2, right? And then we set it to 0 because that gives you the minimization condition, right? So I have given partial derivative because first time you will do with respect to C1, and then second time you will do with respect to C2, and then both of them going to be 0, right? Now if you do this, and then we get a algebraic equation, so 2 by 2 matrix, and then if we form a secular determinant 2 by 2, and then that goes like 0. I'm not writing in detail, so it's going to be 2 by 2 determinant. And if you solve this for non-trivial solution, non-trivial means C1, C2 are not going to be 0, then this determinant has to be 0. Now once you get this, you get the value of C1, you get the value of C2, and then when you get this, right, then what you do, you take these values, right, now put it into this expression, and you get the lowest, best possible MO what we get, right? So that is what the linear combination of atomic orbitals to form the MO, right? Now for sigma, for a hydrogen molecule, of course, like sigma, if you are thinking about that, is going to be a plus combination, right? So I hope all of you remember this. So that is going to be something like plus combination, and these coefficients are going to be something like 1 by square root of 2, right? So that is this, and then I'm going to have one is A plus one is B, right? So I hope that gives you a little bit of idea what we do it for the linear combination, right? Now sigma star is of course going to be minus combination, but coefficients are going to be like 1 by square root of 2. That is because C1 is going to be for anti-bonding orbital, that is going to be half plus square root of 1 by square root of 2, and this is going to be minus 1 by square root of 2. So that minus goes here, and that gives you the minus combination and anti-bonding. Because the orbital wise, if you want to look at, then the plus combination is going to be something like this is 1s A, this is 1s B. Now they are in the same phase, so when you combine them, then the resultant is going to be something like a dumbbell shape, right? So that is plus combination, you are going to get it. And of course, when you go for the minus combination, you get something like this. Sorry, my drawing is not that good. So if you are going for this is plus, this is minus. So this is sigma, and this is going to be sigma star. So that is anti-bonding, and that's what we know, right? So with this much introduction, let me come back to the one which we really want to go for, symmetry adapted linear combination, right? So now we do it very stepwise manner, how we really do it. Okay, so constructing the molecular orbitals using the symmetry, right? Now, here is the question: what is going to be the choice of basis, right? So, choice of basis is choice of basis is something like that. It, as I said before, like it should depend on the problem we are going to solve it, right? And so accordingly, we are going to have the choice of basis, right? When we went for the vibrational analysis, what we did, choice of basis was either Cartesian coordinates or the bond coordinates, right? Now here, naturally, choice of basis cannot be anymore the Cartesian coordinates. It should be like when you are going to form the molecular orbital, it should be choice of basis should be the atomic orbital, right? So therefore, my choice of basis is going to be the sets of orthonormal functions, which are generally the atomic orbitals. We are going to take this, but it can be bonds also. Like slowly we will learn it, but for this class, I'm just going to stick to the atomic orbitals, right? Now, is that any atomic orbitals combined with any other orbitals of two different atoms? Answer is of course no. So we have to think about how they are going to be combined, right? So now what do we do? Basically, we make the orthonormal linear combination of them in such a way that it gives you the irreducible representation of the molecular point group what we are going to use, right? Right. Now we'll come into this in the picture maybe in the next class, because we have only 7 minutes to go, and then we'll stop, right? And then these combinations, which are basically of particular irreducible representation type, are called the symmetry adapted linear combinations of atomic orbital wave function. So that's why it is better to say SALC AOs, right? SALC from atomic orbitals, right? So that's what we'll do it, right? Right now we may be a little bit wondering how it should go, but we'll do it stepwise, right? Okay. Now to do this, we need to take help of some tool, and that is called the projection operator, right? So before getting into the procedure, let me give a little bit of introduction about how this projection operator mean. What does projection operator mean? Like this tells nothing but the proper way to combine atomic orbital functions on individual atoms in a molecule into MOs, right? What should be the proper way of combining that? That's what it should be. So projection operator, it says if we project an MO, which is final molecular orbital, into the atomic orbital bases, right? So if we take the atomic orbital base as a basis, and if we project the final MO, that gives the corresponding components of each individual atomic orbitals, right? Let me tell you what I mean is that, like if I just simply think about, let's say simple Cartesian coordinates, right? So this is X and this is Y, right? Now any arbitrary vector, right? And let's say that is this R, right? Now we know that this arbitrary vector can be written in terms of the linear combination of components of X and components of Y, right? So that is something like this. This is a vector, right? So that is, let's say, AX plus BY, right? So we are taking the components of X, components of Y, and then we are taking the linear combination forming the resultant M. Now, how do we found this value? Now we take the projection of this vector onto the x-axis, right? So from here to here, that is going to be A, right? And then on y-axis, this is going to be B, right? Now exactly in the same fashion, like if you are going to go for the, let's say for the hydrogen molecule, and our sigma, it was ground state, so 1 sigma, that is like 1 by square root of 1s A plus 1s B, right? So now instead of R, if I take 1 sigma, right, and this instead of X, if I take, let me change the color so that should be, so this is 1 sigma, right? And then if I take, this is 1s A basis, atomic basis, and this one is going to be 1s B, right? So if I take the projection of this on the 1s A and 1s B, I should be getting this number, what was 1 by square root of 2. So that number is going to be, so that means A is going to be here 1 by square root of 2 for the X component, and here also exactly you get the same, right? 1 by square root of 2. Now if I go for the minus combination, right, that means for sigma star, right, so that is sigma star combination, right, sigma star, this is going to be a minus combination, so this value is going to be 1 by square root of 2, but this is going to be minus 1 by square root of 2 for that case. So that gives you the projection idea. So this is kind of the projection operator. It works for the how do we really combine the atomic orbitals, or what are going to be the coefficients of the atomic orbitals to form the MO, right? And that gives you the idea resultant MO. Now here, although we use the projection operator, but that depends on the symmetry, based on symmetry, right? So that's what we are going to use this, and we'll be able to tell you very slowly how this SALCs are going to be formed, right? So the formula, the projection operator, it goes like this. Right now, don't worry about this. I'm just giving you like some idea. So this is the atomic orbitals. I'm taking the projection operator operating on this. So that is symbolically, this is the projection operator, this is the basis, and we finally get the MO, which is symmetry adapted. Now I stands for here symmetry. If I go for a water molecule, then this can be of different types like A1. So therefore this is going to be A1, and these characters are going to be for the A1. Then we get the adapted function, which is going to be A1 type, right? Okay, so we'll come back to the next class and we'll do it slowly. So time is just up. So we'll stop here. It will take me out. And finally, if you have any question, we are going to discuss that, right? So stop sharing this. Once it disconnect, I'll come back to you for the question answer, right? Okay.